this video, we're going to do a little bit of an interesting example where we're going to take the standard Cobb-Douglas utility function and we're going to add a subsistence level that you need of one good, otherwise you're going to die. And so the way to build that in, so we're going to assume that consumer has income M, goods X and Y, the price of good X is P, we're going to call the price of good Y Q. And the utility function, when you build in this subsistence level here, D, if X is not at least as large as D, then this term is going to be 0 or negative, and we just assume that the person's going to die at that point. And we have our standard budget line over here. So with the standard Cobb-Douglas, we have alpha and 1 minus alpha, where alpha, we're just going to kind of write it as A, although as I write this, sometimes I might switch and write the A a little bit more like an alpha. Please forgive me if I do that. So when we solve this, it's good to keep in mind what our standard Cobb-Douglas problem solutions are going to look like. If we're going to first derive the regular Marshallian or Walrasian demand functions with a regular Cobb-Douglas function, we did this in a recent video. I'll add a link to that in the description of the video below. You get that the normal Cobb-Douglas without this subsistence level functions are that A times your budget over P, and then 1 minus A times your budget over Q. And the way to interpret this is very important when you're doing these problems. It's very important to understand that what this A means is, say A is 0.3. What you're doing is you are allocating 30% of your budget, if A is 0.3, to buying X, and the other 70% of your budget to buying Y. The amount of X and Y you actually buy just depend on, well, if I take 30% of my budget and divide it by the price of P, that's how many X's I'm going to buy. If I take 70% of my budget and allocate it to spending on Y, divide it by the price of Y, that's how many Ys I'm going to be able to afford here. So we're going to be looking for something similar to this whenever we have this subsistence level, but there's going to be a little bit of change. There's two other things that we want to try to do in this problem. I'm going to do the first two in this video. So we're going to derive the Marshallian demand functions, and then we're going to derive the consumer's indirect utility function. And all that means is, if you look at the mother of all consumer theory handouts that I made, in order to take Marshallian and get the indirect utility function, all you do is you substitute the X star and the Y star from those Marshallian demands back into the utility function, and then you might want to do some simplification, okay? And we're going to do that in this video. The third thing, we're going to save that for another video, is suppose that the government puts a proportional tax on good X. We want to figure out how much would we have to compensate this consumer to get them back to the old utility level. And I feel like this video is going to be long enough doing the first two things and figuring out the compensating variation. It's not going to be that difficult, but in order to get it in a nice simplified form, it'll take some time. So we'll split that off into a separate video for those of you who are interested in doing that. But let's look at the indirect. This is the standard indirect for a standard Cobb-Douglas. And I want you to see how this works, because we're going to see something similar in this problem where we have this subsistence level. You just, again, plug these solutions for X star and Y star back into the utility function. And again, for the standard problem, the utility function is just X to the alpha times Y to the 1 minus A, or 1 minus alpha. I told you I was going to switch between writing those two different ways. So you just plug that in there for X, right? Plug that in there for X. Plug the Y solution in there for Y. Raise it to the 1 minus alpha. Now it's important to see that there's a good simplification you can do here. If we group this M to the A and this M to the 1 minus a, we can distribute. Basically, we can distribute these exponents. Since everything's multiplied or divided in here, we can distribute the exponents to everything on the inside there. Let me do that so that you can see what I'm talking about. So we can distribute that as a to the a times m to the a, right? And then raise that to the 1 minus alpha. Let me do that in red, 1 minus alpha. And that to the 1 minus alpha. And then we'll cross that off. And then p to the a and q to the 1 minus a, or alpha, depending on how we feel like writing it. So since we have an m to the a and an m to the 1 minus a, we can collect those into just one m and then kind of rewrite everything as you see here. When we get our indirect function, we're going to be looking for something that kind of looks like this, but it'll be a little bit different with the subsistence thing going on. Okay, now finally that we kind of see what we're looking for, but it's going to be a little different. Now let's dive into the problem and see how to set this up. Now, marginal rate of substitution. You can do this with Lagrangians if you want. It's just going to save us a little bit of time cranking through a little bit of math. If we skip the Lagrangian nonsense, I'll put a link in the description of the video below where I show that doing it this way is exactly the same thing as doing the Lagrangians. So we want to set up our marginal rate of substitution, which is just the marginal utility of x divided by the marginal utility of y. And we can take the derivatives of this utility function here. I'll just highlight that in pink, and I won't highlight it anymore. I'll just say the pink thing. We take the partial derivative of that utility function with respect to x. We divide it by the partial derivative of that utility function with respect to y. It simplifies down just the same as doing this for any other Cobb-Douglas, really, except instead of having an x, we have an x minus d here, right? We just have an x minus d. So it's going to look the same as any other marginal rate of substitution for any other Cobb-Douglas, and we can just write that down like this. It's going to be the exponent a times y on the top, same as with any other Cobb-Douglas, and then it's going to be x minus d. So that x and that minus d, they just stick together through the whole process of taking the derivative and doing the simplification, and then multiply that times that 1 minus a. So that looks very, very similar to marginal rate of substitution, how it would look like in a standard situation. And we just set that equal to p over q, right? Okay. And our second equation is just the budget equation. And our standard operating procedure when I teach this is we want to solve this equation 1 for y and then plug it over here for y into the budget line. And we can kind of see what we're going to have to do to solve this for y. We just want to kind of get rid of the a on the top and get rid of the x minus d and the 1 minus alpha on the bottom. So we can multiply both sides by the inverse of what we want to get rid of, right? A on the bottom and x minus d and 1 minus alpha on the top. I really need to decide whether I'm going to write these as a's or alphas, right? Shouldn't I? Okay. I'm going to do my best to start writing a's here, okay? A and a. Okay, a. And then we'll do the same thing to this side of the equation so that we keep it an equation. Multiply the bottom by a and the top by x minus d times 1 minus a. All right, and that'll give us y. So we'll just write it real quickly here. Okay, now we're going to plug that whole thing into the budget equation over here for y, and then we'll see what starts to simplify. So we can see right off the bat that this q here and that q are going to go away. Another thing that we can see, let me finish the rest of this equation, equals m. Another thing we can see is that there's a p here in a numerator, and there's a p multiplied times everything else over here in this side. So since that p is multiplied by everything over on this side and everything in this other part that's added to it, we can just divide both sides of this equation by p and cancel that. So we're going to cancel that p there, we're going to cancel that p, and we're going to divide m by p over there, divide our budget by p. Now let's rewrite what we have here so far. So we have x plus, and then we have x minus d, 1 minus a over a equals our budget divided by the price of x here, p. And the next thing I want to do is I want to somehow get these x's together here, right? So I want to get that x there and that x together. The easiest way I see to get those x's together is this x is divided by a. So let's provide a common denominator here. Let's multiply this x by a over a. So now we have ax over a, and then all that can go on the same numerator with the same denominator. And now we can see if we can simplify that numerator a little bit more there. So we have ax plus, here's x times 1 minus a, okay, plus x times 1 minus a. And then we have minus d times 1 minus a, all over a. We can see here that ax plus 1 minus ax, you can see that the ax and the minus ax are going to go away. So we're just left with 1x over here equals m over p. So let's rewrite that over here one more time. So here we have 1x, and then over here we have minus d times 1 minus a over a. So x minus d times 1 minus a over a equals m over p. Oh, sorry, that's x over a there. I apologize for that. So those are all still on the numerator of that equation. And so now what I want to do is just multiply both sides of this by a. So let's do that. And then we're going to get rid of that a in the denominator over here. And then all that's left to solve this for the optimal amount of x is add d times 1 minus a to both sides. So we're going to have here x equals ma over p plus d times 1 minus a. Now again, just to simplify this a little bit, and this is going to lead us to some interesting insights when we do this. And I'm sorry I'm taking so long on this, but let's combine all these with one common denominator. So let's multiply the top and the bottom. We're just multiplying by 1 there. And then that allows us to rewrite this as x star equals, and I'm going to am plus, and I'm going to multiply this out, dp minus adp all over p. And I'm going to simplify this one more time, because if we don't, we have nothing but garbage that we don't understand what it's actually doing. But with a little bit more work, we can actually make sense of this. Bear with me for one more minute. So let's combine these a's. Gosh, I'm terrible, aren't I? Let's combine these a's, and let's write it this way. X star equals a times m minus dp. And then what are we going to be left with? Well, we're going to be left with this thing here, dp over p, and well, those p's cancel, so we have plus d, and then all that is over p. Why is this a better way to write it? Let's look at what our standard Cobb-Douglas solution says, that we're going to take a specific portion of our budget, right, the proportion A, and we're going to spend that portion of our budget, say 30% of M, on good X. Here we see the same kind of thing. So remember now, if that A is 0.3, we're spending 30% of our budget, but not our whole budget. Why not? Well, because we have that subsistence level that we have to buy. So how much X star are we going to buy? Well, we're going to start by buying the subsistence level, otherwise we'll die, right? So we're going to spend some of our money on that. How much money are we going to spend if we're buying D units of X? Well, we're spending dp, that amount of X times the price of X. So after we buy D units of X, we take the rest of our budget, which is going to be M minus dp, and we spend 30% of the rest of our budget on X. How much X will we buy? Well, it's however much money that is divided by the P, right? So this is very similar to what we get for our standard Cobb-Douglas solution. So I hope that makes sense. Now, let's see what our solution for Y is going to be. You might be able to intuitively figure this out, but if you can't, let's slog through the math. So, as usual, the normal, easiest way to figure out the demand function for Y is to take our demand function solution for X after we have it all simplified, and then go back to our equation over here that we solved that tells us how Y relates to X. So this equation right here tells us how X and Y relate to each other. All right, so here we have those two equations right next to each other. And so let's start plugging and chugging. So we're going to plug this X in here. So we have Y equals P times this X, which is A M minus dP over P plus D. Over here we have this minus D. So those two are going to cancel right off the bat. And then all that's multiplied times 1 minus A. So 1 minus A. And then in the denominator we have QA. Okay. Let's see what's going to simplify here. We have a P over here, and then we have a P down here that, after we cancel these, is multiplied times everything on this top row. And so we can legitimately cancel that. Now let's see what we have left with all those cancellations so far. Y equals A times M minus dP times 1 minus A over QA. Well, now we see that we have an A that's going to cancel. And so now we're left with something that is pretty simple. Y star equals 1 minus alpha. I'm just going to put that on the front here, times M minus dP over Q. Now this is very, very similar to the same idea that we had for our demand function for X. Let's go put them next to each other and see. So how much Y are we going to buy? Very similarly to X. We don't have to buy a subsistence level, so we don't see the D over here, right? No D, but we're just taking this 1 minus A proportion of our budget that's left after we buy D units of X, and we're splitting it. So M minus dP is kind of our disposable income after we buy D units of X, and we split it with A, the proportion A, going towards X, and 1 minus A going towards Y. Very cool. It looks very similar to our standard solution with just this one little complication. We're spending some of our money on the subsistence level for x. Okay, now that we have our x star and y star, now let's figure out the indirect utility function and simplify it a little bit. So all we really want to do, let me take the shortcut here and use the lasso tool here in OneNote. So we're just plugging that in, and we're plugging the y in. And thank goodness, immediately these d's are going to go away. So basically that amount of x that you have to buy for the subsistence level just to survive doesn't actually provide any utility. And again, this indirect utility function, we're just trying to come up with a function of how much money we have, the price of x and the price of y, that will tell us how much utility we get. So we cross off those d's, and we're going to end up here with u equals a times our disposable income. I think that's a good thing to call this. M minus dp over p raised to the a times 1 minus a times that disposable income raised to the 1 minus a. Okay. Now, very, very similarly to the standard situation that we were talking about before, without this subsistence level income, what we're going to be able to do is we're going to be able to combine the disposable income here and the disposable income here to the first power, since the a and the 1 minus a are going to add up to 1. And then I'm just going to distribute the exponent to the other things inside the parentheses here, right? So 1 minus a, 1 minus a, 1 minus a power. And when we do all that and simplify it down, we're left with this. A to the a over p to the a times, since everything's multiplied here, we can put q to the 1 minus a and 1 minus a to the 1 minus a. And then we just have m minus dp to the first power here, our disposable income. So this is our indirect utility function. And again, let's just have a quick look at what that indirect utility function looks like in the standard case. We see that these two things look very, very similar here. The only real difference being that instead of just having a plain old m, here it's as if some of our money is being taken by this necessity to spend some money, dp, on buying d units of x. Very interesting. I want you to think about the answer to this next question. If we put a tax on good x, how much income would we need to pay to compensate the consumer to get back to the same utility level as if we were not taxing x? Now remember, there are two different x's that this person's buying. They're buying the subsistence level, and that subsistence level they buy is not going to change because of the tax. So we're going to have to compensate them for the tax on the subsistence level. But then there's going to be another part that we're going to have to compensate this person for, and that's going to be related to the fact that if the price is going up on P because of the tax, their disposable income's going down. So that's one source of the utility decrease. The other source of the utility decrease is going to be the fact that they can afford less X now that they have the tax. And that's how we're going to come up with a solution for part 3 next time, if you're interested in that. So, this is a very long video. I'm going to end it here. Think about your answer to this question, and I will try to come back to it very soon and show you how I think through the solution to this compensating variation problem. And as always, if you have any questions or comments, please leave them down below, and I look forward to talking to you, and I wish you the best of luck in your economic studies. Bye-bye.